assume that they have a, you know, an area around that where they say, no flights.
Hi. Well, the FAA sends out what's called a NOTAM, and a NOTAM is like our warning that
Yeah.
this could.
Yeah.
Notice to airmen.
Mm.
Is that what it stands for?
No.
It is.
Oh, makes sense, I guess.
Yeah. All my time in the Air Force was spent in a medical facility, so.
Are you a MD?
No, oh God, no. I was a pharmacy tech.
Okay.
We used to call ourselves the Phil Fisher Group.
See, you got all the good drugs.
Yeah. Yeah. Well, the great part about it was I used to eat pretty good. I used to have good turkey for Thanksgiving and stuff because one of the chefs or cooks had a intestinal distress problem that I helped him with some antacids, which were over the counter anyway, but he went through a lot of them. And so I drained some, you know, and I did a turkey every Thanksgiving. So it was a good trade-off.
How you doing, Doug? All set?
Yeah, I think we probably ought to let a little more time here since we usually have a few stragglers. Yeah. Oh. I think we're getting into the dog days of summer. I think I heard from Jan, and she's not going to be here. I don't know if she's still feeling bad, but she said she had something to do with family. Has anybody else heard from anyone?
I have not.
What about Angel? Is he around?
Oh, he can't make it this time.
Okay.
Well, just while we're waiting, I still haven't heard anything back from our supposed mirror fantasy.
Well, we were talking about that on the way in.
Yet another email.
I hope it's not going to turn into one of these things where it's, you know, it's always 1 month away from being delivered.
Actually, I'm gonna, now that school's off a little bit, I'm gonna start working a little more stringently on that. And get
Remember,
ready
I'm
for-
missing one of those
Yeah.
things.
Yeah.
So I figured I'd give it to you.
I was making another one, Dana. There you go. Thanks for getting that done. All right.
Yeah.
Where was the wasp nest?
Oh, right. You know, you go into the door from inside to the observatory area. It's right, maybe right here next to the door.
Up above the tools on the wall?
It's like right on the railing of the roof before the wheel, between the above the gap that the
Okay.
wheels happen.
I know where it's at, yeah, but that would be.
How big was it?
The nest, looks like that.
Well,
The thing is, I got stupid and I put the ladder on that side to climb up onto the roof, and then they didn't like me over there. So
need to get some wasp spray out there.
hopefully they're dead because I soaked them, and that stuff works on wasps.
The bumper thing.
I think I have some wasp spray. I used to get them in the where the porch light, that little recess that my porch light was in. They built desks in there. I have to go out and spray them every once in a while.
Need some orange wallows out there.
I'm sorry, My ears are so bad, I feel like I'm at the bottom of a swimming pool listening to people talking outside the pool, outside the water, so you gotta
Yeah.
talk a little louder if you need me.
It's like, I forget what he said, but it's, yeah. Been there, done that. My shop just got loads of flying critters.
Yeah.
Howdy, sir. Are you a member?
I am. I've been a member for several months, but I've never participated in
Oh,
any
great.
event.
What's your name?
Mike Baldessaro.
Mike,
I
okay.
moved to Topeka in February and was formerly in Southeast Kansas, Independence, Kansas.
Great. So glad you had a
Thank
meeting.
you. Yeah.
They're open to the
Finally
public.
made
We
it.
don't know if our, members are coming or the public's
Yeah,
coming.
Yeah, yeah.
So have you ever been out to Far Point or
I have
anything?
not. I have not. I've been in the process of moving and selling my house down there
Yeah.
and all that, so.
So you're in the Greenbush area.
Yes, that is right, Greenbush area. Yeah, that would be east of me, yeah.
So, do you have equipment, telescope?
I
equipment?
have the Celestron 9 1/4 Smith screen.
Oh, that's nice.
Yeah, nice.
So we have a members, we don't put that information, members nights on our website, but they come to you in the group IO email. Do you get those?
I do, I get all the email.
Okay, so we have one this Saturday, and it's clouds or no clouds, and we're
Okay.
doing some training on some astronomy software and
Out at the.
out at Farpoint,
Oh,
which
okay.
is, if you haven't been out there, the way to try to find it is go to Mission Valley High School.
Yeah, okay,
And then there's a side road
uh-huh,
that heads north
yeah,
on the west side of the school. You
Okay.
just follow that past the football field,
okay,
and you'll see some buildings, and that's us. We're at the end of that road.
okay.
There's a-
Mission Valley High School.
Go to Mission Valley High School,
Uh-huh.
which is,
Yeah, I Googled it once, I know about where,
yeah,
generally,
it, yeah.
Mission Valley.
So, some people have trouble finding it if you just go by the address. But, and then once they get out in that area, they have trouble finding the observatory. So,
Okay,
there's a dirt road on the west side of the school.
uh-huh,
What's it called, Bozard or
Something like
Bodart?
that.
Bozard.
yeah.
Bodart.
Bodark.
Bodart.
Uh-huh.
And so anyway, it's a dirt road. You just follow it, go
Did you
past
say
the
that was
football
north?
field,
Uh-huh,
and we're on the dead end. We're on the north side of the football field.
okay,
Some roll-off roof buildings. They're not domes, they're roll-off roofs. They're,
Okay.
they're what you see on the NEKAAL website picture.
okay.
Okay, so it's
What
nice.
time do you gather out there?
Well, your
Seven, isn't it?
Your presentation starts when?
This is Saturday, this is this Saturday, right?
Yeah. Yeah, because we just kind of replaced that with, observing sessions, so. And if we're not gonna be observing much, it sounds like, so we could meet at 7 and get out a little bit earlier that way.
Okay, I'll try to make it.
Yeah.
Is it this Saturday? you said?
This Saturday.
Yeah, and I know I've got an email about it.
Yeah, and then we have public nights once a week. I mean, once a month,
Mhm.
and those are on the schedule.
You're probably gonna come to this.
You guys think we ought to go ahead and get started, actually? I guess we kind of have, but welcome, everybody.
Okay.
I don't know, do we need to go around the room? I think we all kind of know each other, don't
On the
we?
far side of the school.
Yeah.
Okay.
Who's that guy over there?
This is Mark. Mark is so anyway, welcome.
Thank you very much.
I think we probably exchanged some emails. I'm Doug Gooden.
Uh-huh.
I think we probably exchanged some emails, but good to meet you in person.
Thank you very much.
And couple things just to talk about here. Should we turn the light off?
Yes.
One of the- So obviously, general meeting, you're here, so you know about it. The next one actually is on the 22nd of September. That's actually the equinox, which kind of astronomically important. So we'll be meeting on the equinox. This is a thing that most of you probably already know this, but the next public night is September 3rd, right? Wait a minute, that's not right, isn't it?
That's right.
Yeah,
Is it
we-
right? Okay.
We
Yeah.
switched it around because of, we wanted to go to the moon cycle.
Right, and that's a week from Saturday.
Yes.
Yeah.
So we have Saturday, this upcoming Saturday, this weekend is a members' night,
Right.
which, as last time I looked at the weather forecast, it wasn't really all that favorable, so may not be any observing, but Gary, as we mentioned, Gary's going to do a presentation on Tyco Tracker. It's a software package that does a number of things.
Just say I'll lead discussion, not necessarily that I can teach anybody anything. but-
And that's actually going to be streamed too, right?
Yeah, I think so. I don't know. I guess.
I'm kind of
There
hyped.
was some talk about that.
Yeah, we could try doing that.
Okay, I'm kind of hoping so because I have house guests that night that kind of keep me from leaving. So I'm hoping to kind of come in on that virtually. And then the next public night is September 3rd, and that's a little bit out of sequence from what we've been doing. It's and the reason for that is that's the first quarter moon, and that'll give us some kind of more interesting things to show people. So on that topic, and again, this is something that Dave has been sending emails out about, but I thought I'd go ahead and add this. There's always things to be done. And so if you've got the ability to get out there, we can certainly use the help. There's a number of kind of jobs basically to do. The telescope operation jobs, I think, Russ, you probably have been running the 12, right? Tomball's offline, so we don't have to worry about it. Dave, are you still planning on it, or you kind of
I
depends on how
kind
you
of keep
feel?
my name there, but the thing on the 12-inch, we are looking to train our members on our own equipment out there. And one of the first pieces that we train you on is how to operate the 12-inch.
Yeah.
Russ, one of our superstars, he always seems to get tied to the 12-inch. So if anybody wants to come out there, Russ can give you some training on the 12-inch, and either you can continue to help us on public nights, or after you've been a member and active for a while, we can give you some keys and you can actually go out to Farpoint and use the 12-inch on your own. And we also are developing the ability for the 12-inch to be remote. So we offer training and then access to active members, so we like to pass out keys, but we also kind of have a set requirement to kind of control our facility as much as possible. But we like to have members active. And so this is a great way, not just through the 12-inch, but to come out on Publix, just hang out. And, you hear things, you learn things. I'm no expert on anything, but I love listening to the smart people in this room. So we definitely use help.
Yeah.
So we have 35 members, but roughly a third of that, if we're lucky, are active people helping us out.
Yeah.
So we like having people come out, members nights, public nights.
And I think there's something to do for pretty much anybody that wants to. So kind of encourage that. It's a good opportunity to kind of get to know people out there too. We had pretty good turnout the last public night that we conducted. Though the one this past weekend we did not. We canceled it basically because the sky conditions were not very favorable. So anyway, so if you can make it out, please do. It's like Dave said, we can use the help. Just if nothing else, just keeping everything organized and moving, basically, and watching what everybody's doing, basically. Okay, so that is a week from Saturday, right? My sense of time is, I don't know. We started again. Classes started again this week, which is always kind of a shocking week for me. I go from not doing very much to all of a sudden doing a lot. Okay, new stuff this week, and again, this is just stuff that kind of caught my attention. This is one I thought was pretty cool. The Webb telescope is now fully functional and being used, and it's actually been detected carbon dioxide in an exoplanet atmosphere. I'm going to talk about exoplanets tonight, so a lot of my news is related to those. It was actually found in a type of exoplanet called a hot Jupiter. It's a gas giant that's really close to its primary star. So it's, you know, it's not really any kind of a bio indicator, which, as we're going to see, that's one of the, you know, looking for certain kinds of atmospheric constituents is one way of looking for life, basically. But so this is certainly not that. But what's kind of useful about it, here's actually one of the spectra, and you can kind of see the carbon dioxide features in the spectrum here. What's noteworthy about this for me is that it shows that this instrument can actually analyze the atmosphere of an exoplanet. Of course, exoplanets like this are almost all atmosphere, but still, it's a kind of a noteworthy thing. So this one sort of caught my attention. This was actually from, I believe from Physics Week or something was where I saw this article, but this was one that really sort of caught my eye. Another one is possible, again, an exoplanet that's covered with water. So here's the, oh, that's the wrong one.
That's the same one.
That's the same one. No, that's not right. This is a different, sorry. I put the wrong graphic up here. Sorry about that. But anyway, this is actually, I believe, in the same system as that previous one. And they actually found a potential near super Earth, basically a large, you know, kind of a similar to Earth, a terrestrial rocky planet, but larger, and potentially covered with water, which again was kind of an exciting thing. The other thing I thought was kind of interesting about this was that the lead on this was a graduate student. So this is a pretty significant discovery made by a young scientist really early in their career. Somebody from the University of Montreal, where I actually spent some time early in my career. Kind of an interesting place, except my French was not good enough to keep me active there. This is one I was actually going to bring this up, but I didn't. Anyway, this was a news item, which this is, you know, we talked a little while back about sonification. It's kind of like visualization, except instead of converting signals into pictures, you convert them into sounds. And so they did a sonification. I kind of wish Dustin was here. He probably would have liked this because it deals with black holes. They did a sonification of a black hole, and you can find it here at this. Has anybody else seen or heard this? Isn't it about the creepiest sounding thing that you can possibly imagine?
How do you know that's what it sounds like?
Well, it's a sonification. It's not really sound. It's just it's just taking a signal and converting it into sound.
Yeah, it's creepy, but
yeah,
I don't think black holes make sounds because it's space.
They don't really. But it's like visualization. It's like, you know, how do you visualize a radar signal, which humans can't see? Well, you just kind of convert it into something you can't see.
Almost any picture you see of any color image of anything is always exaggerated.
Yeah, but sonification is kind of an interesting thing that's happening in a lot of fields now, and it really makes for an interesting way to kind of perceive data, basically. So anyway, I thought that one was kind of
the thing that I don't like is I think most of the public thinks that if they stood next to this black hole, that's what they would hear.
Yeah.
You know, and so I think it's like misleading, false information.
Yeah, well, I think by the time you got close enough to,
Maybe we could ship some of these geniuses over there.
You'd be dead any number of ways. Well, you know what they say, in space, no one can hear you scream, so maybe so. Anyway, I just thought this was kind of an interesting thing. I for a while there was kind of experimenting with doing sonifications of data, and so stuff like this always kind of catches my attention.
Well, what's really interesting about that is our acoustic ability to detect pattern recognition.
Mm-hmm.
So sometimes when you translate the data from one dimension to a different dimension, our ability to perceive the
patterns,
understand it is totally
It's like the
different.
movie Contact. The
Yeah.
movie Contact,
She used
remember
to
the guy
listen
that
to
was
the-
blind but he could hear real well?
Yeah,
Figured out the sound.
yeah. It is a kind of an interesting way to perceive data. So as far as stuff that's visible this month, again, this was a busy week for me, so I didn't have a whole lot of time to track stuff down, but here's a few things. You know, the meteor shower from last month kind of, I wouldn't say it fizzled. The meteors were still there. It was just during a full moon. So I personally didn't see one in the one time I went out, because I was a little early in the night. So that was a little bit disappointing for me, because I kind of missed one of the big, showers. But there's a couple in September. The Delta Argids on September 1st. They're not a very intense shower. There's usually only about 7 or 8 of them per hour, which is not very many, really. What's interesting about them, though, is that they often make some pretty interesting colors. And if you're in a dark sky site where you can see the color, you often see a kind of different colors. And then the Eta Perseids on September 9th. So there's some meteors that are going to be available. Jupiter's going to be on opposition in September 26th, so it'll be a good time to observe it. This is one I kind of liked. Vesta is, number 2, the second minor planet discovered?
Ceres is first.
Ceres is 1 and Vesta was 2, right?
That's right.
So it was the second minor planet ever discovered. It's one of the larger ones. I understand that if you're in a dark enough place and you have reasonably good eyesight, you might be able to pick it out naked eye. I'm not sure about that. But it's an object that is pretty readily visible in a modest telescope or binoculars or something like that. And it's actually in opposition this month too, so it's a good time to observe it. And if you want to own a piece of Vesta, you can buy one for, in this case, 12.5 grams for $124 from eBay. So if you want to see it and then own a piece of it, you can. You can actually buy a little vial of dust from Vesta for about $15. So I thought that would. I was just kind of fascinated by the fact that you can actually buy a piece of this thing off of eBay for.
How do you know it's from Vesta?
It's chemical composition, yeah, it's the one that they're selling is actually from a fragment of a meteorite that hit in.
It's a spectrum comparison, isn't it?
Spectral comparison, yeah. So they look at the mineralogy of it, which is pretty well understood. They've been taking spectra of this thing since the 60s, so it's pretty well understood. And then measure this in the lab, and it turns out they're the same thing. So $124 plus $4.80 for shipping, and you can own your own piece of Vesta. And here's a little bit of an observing challenge. This is number 3, so Vesta is the second one. This was the third one, Juno, and it's at opposition this in September as well. So it would be if you want an observing challenge. I think the number that sticks in my mind is it's about 8th magnitude. So it would be telescopic. You couldn't see it with your eyes, as far as I know. 6th magnitude is usually about the limit that people can see with their eyes. But you could probably pick it up again in a fairly modest telescope or with a pair of binoculars. But it's at opposition, so it's going to be like fully illuminated. So it'd be a good time to see it. I personally have never seen any of these, so I think it would be kind of cool. I think I saw Ceres once through a telescope. So I'm the only one of the main belt minor planets I've actually seen, at least that I knew about.
What can you see? Can you see any?
It just looks like, it pretty much just looks like a white dot through the telescope. You can't really make out any kind of detail on it. I doubt if you could make out much detail with anything telescopic. Oh, that reminds me of another thing I was going to talk about. There is one of the asteroid deflection missions is actually going to do the rendezvous here shortly. Isn't that right? The one of these tests to see if you can actually push one of these things, which is part of the planetary defense.
Okay, you're talking about an impactor that's going to come in and take out.
Isn't there a test of one of those things coming up here pretty soon?
I don't know if it's coming up really soon.
Press is looking
I
back.
thought it was still a ways out yet, but maybe.
But there was something about that I saw, kind of a news item go by.
DART.
DART, yeah. And it's gonna, the DART impactor is, I don't think it's one that's actually capable of moving it. It's just more of a test to see
Well,
what the surface properties are.
what they, no, what they think they can do is they wanna see if they can measure, it's a moon with or a asteroid with a moon,
Mhm.
and they're gonna hit the moon, and they're gonna try to see if they can then measure any change in its orbit around the
Around,
asteroid,
yeah.
So it is an actual test of movement, not just impact.
Okay, does it say in there when it's?
We better hope it works.
Yeah, September 26th. DART is double asteroid redirection test.
Okay, so September 26th, this thing will impact on it, right? And again, this is kind of relevant to some of the stuff that, you know, that the club does, because one of the things that David and Gary are really pretty deeply involved in is actually calculating or helping to calculate the orbits of things that might potentially hit us. And, you know, if you know ahead of time, you know enough ahead, you don't have to move them very far to get them to miss. And that's a lot of what this test is all about. And there's a number of countries now working on this. There's I guess a Chinese program now for asteroid deflection too. So one of the weirder ideas I ever heard was that you go to one of these things and you, instead of actually impacting it, you just basically drop big paint canisters or dyes on them, and that creates a dark spot that'll heat up, right? The solar radiation will heat it up a little more. There's this thing called the Yarkovsky effect. There's a intense radiation stream that comes off that dark spot because it's warmer, and that might be enough to actually push one of these if it's far enough away.
Hit
So-
one side with a lot of white paint and the other side stays dark, because it's normally dark, so you'd use white paint probably.
Oh, okay.
And then you kind of, that way it kind of adjusts the pressure on one side, and it makes it uneven, so it changes the orbit
Yeah,
eventually, over a long period of time.
yeah.
You gotta have a lot of time.
Yeah, you'd have to do this very, very far in advance. But anyway, I thought that was, you know, this interesting idea of painting an asteroid basically to get it to miss. So anyway, but as far as observations go, this is one that would be a challenging one, but might possibly be available for in this month. That's it. Like I said, I was a little short on time this week, so I didn't have a whole lot of news items and observation items to talk about. Has anybody else got anything?
Well, as I said earlier, no news on the mirror yet, but it really should be here sometime in September, and I'm hoping it probably the first 2 weeks of September. So, prepping and getting things ready to go, I've been holding off on, because it's been so hot lately, I haven't really done much. But I'm gonna start getting a little more aggressive with it now and trying to get everything prepped out before it gets here. Hopefully it will be here in September, so
And
that's my goal.
And the problems with it
Otherwise,
are
I'm going to Arizona.
pick it up yourself, and
Yeah.
the problems with it are all fixed, right? The figuring problems that cropped up are all.
Yes.
You said-
Yes, the astigmatism, he said the astigmatism now is totally gone and everything's very smooth now.
Okay.
You should have sent it to the coder by now, right? Or
Yeah, well, yeah, I would have thought that was a thing that, last time I talked to him, I thought it was gonna be already at the coder.
We might
Still
email-
wasn't.
email that coder again.
Yeah,
See if it's
I'll
there.
just wait, I'll just see if I can get him to answer first, and then, because I don't wanna go an end round again. I've done that before, and the coder's going, what mirror? Don't know anything about it.
No.
So, anyway, we'll get some answer from him somehow.
Okay.
And I'll, as soon as I get a reply, I'll let everybody know.
Okay.
Send it out in an email.
Does anybody have any questions about the remaining scopes on the donation list to purchase? There's still some left. Most of the good ones have been picked up, but everybody's got the email, and I tried to update the list to keep you informed. Somewhere down the road, the smaller items, which range from eyepieces to some filters and diagonals and some of that other little tinier stuff. We'll put that list out too, and they'll be cheaper.
If,
Try to do at least half price.
if some of the stuff doesn't sell, is there any sort of plan for it, or do we want to try to?
Well, and this is the
Sell
last
it
board
online.
meeting, I don't know if you guys got that far, but if something doesn't sell, maybe we lower our price or open it up to the people that come out, because some of the scopes that are remaining are not, the whiz bangers.
Mhm.
They're good little beginning scopes. There's a few nicer ones. But some of those are almost obviously beginner scopes. Maybe we give them to some kids or something, I don't know.
Yeah, yeah.
Don't know if you guys discussed that at the last board meeting, but certainly next one.
Yeah, yeah.
Are we having a board meeting before public night? So we have another board meeting in about a week and a half.
Yeah, yeah. Yeah, this one is a little bit out of sequence compared to what some of the others have been. Okay, well, any other news items? Items of general discussion?
I would bring up a little bit about the training session Saturday. We'll probably get into, I took a lot of time and wrote down a whole lot of stuff last night while I was using it to do analysis. So, and I'm gonna bring that out, and that's gonna be my show and tell for it. I'm only exploring Tyco, it's called Tyco Tracker. It's written by Daniel Parrott. It's an amazing program. He did a really good job of getting everything very concise, but very useful and pretty accurate, I think. One of the things that we are not used to that it does is we can eliminate brighter stars in the field.
Mhm.
So, well, actually, about any star that's in our field. Because it just takes, catalog data and says, okay, we subtracted at this point. And anything that's extra is the asteroid. So if your asteroid's coming close by it, it measures basically what it should be and some area around it, but then it also leaves whatever little hump is left is then the asteroid that's underneath it.
Mhm.
It can't work right on top of that star, but seldom does that happen, actually. It comes close to it, and that's about it. So, but it does a really good job of that. So far, I haven't noticed that there's been much deviation from what we used to do versus what we are capable of doing with this. And it's much faster and it's much easier once you get the hang of it.
So for that side of the table, Tyco Tracker is what we're planning to use when the Tombaugh is back together and we get back to doing our NEO research, where we're doing follow-up on asteroid discoveries. We used to use a program called Astrometrica, and Tyco Tracker is much more powerful. So for people that aren't doing the NEO program, we do it with the Tombaugh. Gary's got his own Sandlot Observatory that turns in data. Is like, if any of these guys wanted to use it, is there another use
Oh,
besides
certainly, yes.
asteroids?
There's a lot of uses. One is photometry, just doing variable star work. Exoplanets, it's been pretty useful for a lot of different things. I have used it for variable star work. I've turned in now about 8
So it's doing light
sets of
curves?
night data. Yeah, it does light curves. It does, and the nice part about it is it'll set it up in AABSO data so that your data is saved and you can save it in AABSO format, which is American Association of Variable Star Observers. So, which is a pretty big organization. I actually belong to it. It does a pretty reasonable job. Matter of fact, my data that I sent in, and Doug has seen this. I sent it to Doug because I was just happy.
It was good, yeah, really good.
It was, within probably exoplanet searching range, because it
Yeah.
was down to like 10 millimags.
Yeah.
So
And that was-
that's pretty good.
And Gary has a 22-inch scope at his observatory.
And it's capable of differential photometry.
Yes.
And it actually like picks comparison stars and stuff.
Yeah,
like
yeah.
too.
Yeah, it will actually pick out a bunch of stars and you can decide whether, and it registers those stars and lets you know if it stays consistent throughout your time period.
Right, yeah.
So that you're not picking another variable star to use as your check star or whatever.
Yeah, it's pretty impressive.
It does a good job.
The one problem I've had with it, which is strictly my fault, is that I don't have a Windows computer, and I'm having a really hard time getting it to work on like a virtual machine or anything like that. And it'll run just fine on my virtual computer on a Linux machine, but it won't download the catalogs and stuff,
Oh, yeah, that's.
which you
important.
gotta have, you know. And
You can download those separately though.
yeah, I may need to figure this out before Saturday, so I can follow along when you do.
So
that.
this is mostly watch you run the program on the big TV, and you have some
Yes.
sample data, right?
Yes, I'll bring sample data with me. I'll bring actual data that I took last night, actually.
So it's a $50 program,
Yeah, it's
and
really cheap.
some components of the program have high computer, high graphics card needs.
Yes.
And then some other
I,
things it doesn't.
one of the things that it does do is it allows you to narrow down your search so that you're not looking through the whole sky for in any direction, any speed. If you do that, it takes a tremendous amount of computation time.
So that's if you take an
That's if
image
you're
and you're
taking-
just looking for an
If you
asteroid.
take 100 images.
You wanna
and-
discover something.
And you want to try to discover something in that 100 images. It goes through them all and it does every direction, every speed, but that's really intense.
Yeah.
So you've got to have a really strong GPU, graphics card. You can't really run it out of your CPU because your CPU has other things to do. So a graphics card is kind of open. You can command all of its computing power. So that works out really well.
I think you said you did a run on that at yours, because you have the graphics card?
Oh,
And how long did it take?
about 6 hours
Yeah, that's
with the graphics card.
probably
so,
take about 6 days without it.
Yeah, it's amazing. Actually, you can, and the better graphics card you get, obviously, the quicker it'll be. But I wouldn't recommend this for just doing sky survey stuff, especially once we get our wider camera or our wider telescope mirror, because it's going to take up almost a whole degree, and that's going to increase its crunching that it
Yeah.
needs to do. So.
But you know, I was thinking about that if we took some images that are oriented toward doing the NEO follow-up work, you know, offline we could just run the images
right.
out of curiosity.
Right,
You know?
right.
I mean,
No,
just take them to some,
exactly.
you know, just when we're not
And
actually involved in the.
Yeah, basically you set up and you can set up a nice wide field of view. It goes deep as you possibly can over so many 150 images or how many, and you set it to go and then you go to bed.
Yeah, you might as well squeeze all the information out of those
Oh,
things
yeah,
as you
exactly.
possibly can.
Why not?
Anything come of those K-State computers you mentioned?
Yeah, I have a couple of GPU cards that are no longer being used. They're not by any means state-of-the-art ones. They're several years old. But I think I have to I can't just steal them, you know, I have to go through channels. But
Have to go through channels to steal them.
Yeah. But they may be available.
Anything computer-wise?
The computers are kind of a different beast. I haven't made much progress on that front, actually. I have a kind of a nice machine that I use for modeling that might be able to like use it at night, you know, when nobody else is using it, you know.
Something that's got some crunch power to it.
Yeah, it's a beast. I mean, it's got
Yeah.
I think 4 GPUs in it, so it would crush the crap out of
Well, that's the
products like
thing, and like Russ brought up, is we can stack the GPUs and use them that way.
Well, probably, you know, if we can get those two, if we really can't get those two, the thing to do would be to put them both in the same machine.
Yeah,
right?
well, right.
Well, what kind of graphics card do you need? I mean, does it need to be a recently modern one?
Well,
Some years?
let's just say the more modern ones have a much stronger, what's called CUDA. I
Yeah,
don't know.
the
what
CUDA cores, right.
They have a lot of CUDA cores, and so the more CUDA cores you can get, the better, and of course, the newer ones have a lot more,
Yeah.
so.
Well,
Okay.
That's gotta work out.
Well, because I have an old computer that isn't really functional anymore, and it had a reasonably nice video card,
Yeah.
but that was like 6 or 8 years ago. So I'd have
Yeah.
to see what it is.
Well, and it just, it
And
kinda.
maybe I'll let you know, and if you say you want it, then I'll donate it to the.
Yeah. I think we've got a, I don't know, a 2,000 CUDA core, in there now.
I think the ones we're getting are 6,000.
Yeah.
So they're, I think they're NVIDIA
Yeah.
cards?
Yeah. that
Right.
would be-
GeForce or something like that,
Yes.
but it's not a particularly, they're not new. You
Yeah.
know, they've been, and I don't know how, I think they get a little bit worn out. I think the heat kind of affects them, so I
Yeah.
don't know what the,
Well, I know they have to have a lot of cooling if you get stacked a bunch of them together, you're gonna have to have a big cooler. But
yeah.
they're all a lot more power.
Yeah, and then what is it run on Windows 10?
Mhm.
Okay. There is a piece of software which I've not run yet because I don't have a Windows 10, but I need to change over to that. But it will do fan control,
Oh,
and
yeah.
it will ramp up your CPU
All the
and
fans.
GPU and all this stuff based on certain triggers and stuff.
Yeah.
So I will, I can, there's a video about it from somebody. I'll send you a link, or I'll send it to the.
Send it to Russ because I won't understand it.
Okay,
That's
yeah.
that's cool.
It's a fan control software.
I talk like I know what I'm talking about, but I really don't.
Well, the machines that we replaced, you know, when we replaced these machines, the ones we replaced them with have a cooling unit in them.
Mhm.
So,
Yeah. Yeah, most of the ones you buy now that are any size, they all have their own cooling system.
Yeah. I know it's kind of a large and clumsy box, basically, that's sitting on my desk at the moment. But anyway. So yeah.
Yeah, any of that stuff is, and like I say, kind of, if you got something like that, you know, talk to Russ about it, because I personally, all I know is that you need this, and that's all I know. So, I don't.
It looked like, from the videos I was looking, it looks like setting it up is pretty straightforward if you have one.
Yeah, it is. It is a little time consuming because you do have to set up a lot of parameters as you go. But once you get that done, it flies through pretty fast.
Okay. Well, any other discussion? So again, I have to kind of give a confession here. What with being back on the clock and all, time was a little tight over the last couple of weeks. So a lot of what you're going to see here is basically stolen. Stolen from somebody at, I believe at JPL, who, a NASA employee that did a presentation on exoplanets, and I kind of took it and whittled it down a little bit and added a few things to it. But anyway, I wanted to talk about this, and actually that's their title. This is not so much about exoplanets and the search for life, it's exoplanets and a little bit about the search for life. But it's something that is really interesting to me, and so I kind of chose it as a topic again. That's one of the things I kind of often think about is, you know, I would love to hear your guys' ideas, anyone's ideas on topics, because otherwise you get the stuff I'm interested in, you know. So, so what this is one of the things I'm kind of interested in. So anyway, you know, it was always interesting to me when there was the whole big debate going on about whether or not Pluto was a planet, and are there 8 planets or 9 or 10 or whatever, because even by then there was several hundred, you know, most of them were not in our solar system, but And it's kind of been a gold rush lately. Every time I see this particular graphic, this number has gotten bigger and bigger. The last version I was able to find, which was from 2017 apparently, there were 3,700 confirmed exoplanets. The last time I checked on this, which was I think the day before yesterday, there was now over 5,000, and the number gets bigger every day. So it's been one of the major discoveries and most exciting areas of progress in all of science, but especially in astronomy and astrophysics, because of all the things it implies about the presence of life, the structure of how the cosmos is structured, all of that stuff basically. So these were the statistics as of, I don't know, a few years ago when there were 3,700 of them. The most recent numbers I've seen on these are proportionally about the same, right? Most of the planets that people have found have been very large planets. That kind of makes sense because the bigger they are, the easier they are to find. So this doesn't necessarily imply that
Observing bias.
yeah, it's an observational bias. It's an availability bias. And so this doesn't necessarily mean that, big gas giant planets are, 600 times, 1,200 times more common than these little tiny things. It just means that these are a lot easier to find. But anyway, the point here is that there's more and more of these things being found. And that's one of the things I want to talk about, but I also want to talk about what I think is an even more exciting part of this, which is the field has kind of moved away from discovery and into analysis now. And it absolutely amazes me what astronomers can learn about something it's that difficult to observe. It's a truly amazing thing. It's also not really a new idea. The idea of looking for planets around other stars actually goes back quite a ways. This gentleman right here is Peter Van de Kamp. He was a professor for many, many years at Swarthmore College. Is that in Philadelphia?
Yeah.
It's in Philadelphia, and it's a kind of a very elite, private, liberal arts school, basically, and this guy basically was the astronomy professor there. He had access to a pretty good telescope and a pretty good camera, and he spent literally years and years photographing a few stars, including Barnard's star, which is one of the closer stars. And he believed, and in fact announced in 1962 that he'd found evidence for a planet around Barnard's star. What he was trying to do, his methodology was actually, the concept behind it was actually sound. What he was looking for was tiny little wobbles in the position of the star, right? Because anything that has a massive object orbiting around it, it's going to get tugged around a little bit. And even if it's a, relatively small planet and a relatively big star, it'll move just a tiny little bit. And he thought he had found evidence for this. This is an astrometric method, right? He's trying to make very precise measurements of it. Unfortunately, the capability of his equipment was just not good enough to detect the kinds of size dispersions that he would need. So he didn't find anything. Turns out Barnard's star actually does have a planet around it, but it's not the one that Peter Van de Kamp thought that he had. But the idea was really sound, and it kind of shows you that there was interest in all this for going back quite a ways. I've never actually read this book, but I think I might put it on a reading list at some time because it sounds kind of interesting. So you often hear that the first exoplanet ever discovered was in October of 1995. That's not exactly true, actually. That one was this thing called 51 Pegasi b. That is not exactly true, though. There was actually one that was discovered in 1992, but it was orbiting around a neutron star, or a neutron star, kind of a degraded old star. And it was found by radio techniques. It was found by radio astronomers, but it's been confirmed that it's there. So in a way, you could say that the first discovery of an exoplanet was really in 1992. The one in 1995, though, was the first one that was really around a sun-like star. It was found by two Swiss astronomers, Michel, I can't think of his name now, Didier Mallows and Michel Mercot, I believe. These two guys actually won the Nobel Prize year before last, I believe, for this discovery and some other things. But they found this thing around 51 Pegasi b. It was the first discovery around a sun-like star, basically. So, pretty big deal. It was a type of exoplanet called a hot Jupiter, and it was a big surprise because it was really big and really close to its star, right? So close that, you know, much closer even than the orbit of Mercury is to our sun. And that was a pretty big surprise because, you know, most of the theory about how solar systems formed basically ended up with little planets, little rocky planets close to the star, and big gas giant planets away from it. And so, of course, we just assumed that's how it worked. And this really upset a lot of apple carts, right, from the very beginning of the thing. But it was a pretty notable discovery. Probably, I would think, you know, when people make lists of the most notable discoveries in science, this one will be high on that list, prominent on that list. So this was the first detection of that in 1995. So it's been, what, close to 30 years now.
So did they use photometric measurement?
They've actually used, they didn't use photometry. They used radial displacement. Actually, I got some slides about that too. Actually, they used the same idea that Peter van der Kamp used, except they just had a much more accurate way of measuring the movement of it. And so that's actually a good segue, because I wanted to talk a little bit about how you actually find these things, or how you sort of discover them. And the problem is that, you know, you're trying to look for small, relatively small, dark things next to relatively big, bright things. And someone once compared it to, you know, trying to find a firefly next to a searchlight. That actually might be easier, because fireflies at least make their own light, right? Stars or planets, not so much. And it basically means that direct observation of them is pretty difficult. So most of the methods for actually detecting the presence of exoplanets are kind of indirect ones. There are some direct ones. You know, there's a nice, I didn't do this, but you know, there's a nice animation there that kind of shows the problem. So there are some, actually this might be the wrong set of slides, damn it. There are actually a number of different ways of detecting these. There is one that's sort of direct observation. You see, it is actually something that is being used. Of course, the problem is that, you're trying to find that thing next to a really bright thing. So if you can kind of blot out that bright star, maybe it might be possible to see the dim little objects that are around it. So some pretty interesting ways have been sort of proposed to do this. One of them is just putting a thing called a coronagraph on the telescope, which is just a little block thing that blocks the star, right? It's named out because they are used for studying the solar corona, right? So you block out the sun and you can see all that gas around it. This is similar to that. Another one I think is pretty interesting is this kind of star-shaped thing. This is obviously a proposal for something in deep space, and they'd actually be able to use this star-shaped thing as the blocker, as the occulting object, and be able to look at that. There have actually been some successful applications of this. This surprised me a little bit, because I always thought you can't do this, right? It's just technologically too impossible. But this is actually a direct observation of the solar system. You can see they've blotted out the central star would be right in here, using a coronagraph type device, basically, and then you can see some planets around it. This is actually a part of a series of images that were taken, which, when I kind of looked this up online, there was actually an animated version of this, so you can see the little objects moving around. So direct observation is possible, but there's some it's thought to be some pretty significant theoretical limitations on what you can actually see. They probably have to be fairly large planets, and they probably have to be fairly far away from their star in order to be detectable this way. But there have been some discoveries using direct observation. The method that was actually used to first discover one of these is called the radial velocity method. And it's akin to the thing that Peter Vanderkamp was trying to do, except he was trying to astrometrically measure the movement, like, actually measure position. What the radial velocity measurement does is it uses redshift in order to kind of detect that movement. So if you can imagine that star kind of wobbling around a little bit, right? Some of the wobbles are towards you, some of the wobbles are away from you. The ones that are toward you are going to shift wavelengths of light just slightly into the shorter end of the spectrum. The ones that are wobbles away, right, the velocity is away from you, is going to shift them to slightly longer wavelengths. And if you've got a sensitive enough spectrograph, you can kind of measure that, right? So here's this sort of simple diagram. There's our exoplanet. It's obviously a little bit exaggerated, but it's moving the host star around a little bit, so you're getting some red shifting and some blue shifting. If you can kind of think about this star as actually orbiting around the common center of gravity between these two things, then that kind of explains how you see this shifting. And this is actually the technique that was used to measure to find or confirm the presence of that very first exoplanet. So here's some of the data that Michel Mayor and Quiros used for this, and you can kind of see the radial velocity here kind of shifting. Notice the speeds here. This is meters per second, right? It varies between what, maybe 10 and minus 10, right? So you think about how fast everything's moving out there. The difference in this is 10 meters per second that way, or 10 meters per second. 10 meters per second is not very fast. I mean, you can walk that fast pretty easily. So, and so that means those shifts are not going to be very big either, those little wavelength shifts. So take very, very precise measurements and very, very high quality spectral equipment to actually do this. But this was the technique that was used to actually detect that very first exoplanet. So another method is photometric. Gary kind of alluded to this earlier. The other method that's used to detect them is photometric methods. This is also sometimes called the transit method. And the deal here is you can kind of see that some planet passes in front of its star, right? As it passes in front, the light from the star goes down just a little bit, just dims slightly, and then brightens back up again. And that dimming and brightening produces a very kind of characteristic light curve. And so these light curves can be used to not just detect the presence of planets, but also tell you something about how big they are, how fast they're orbiting their star. You can even tell something about the atmosphere of them from if you've got sophisticated enough photometric techniques. So this is another one of the methods that's used. And this is actually the one that the exoplanet detecting satellites that are using, like the Kepler satellite we'll look at here in just a second, or the TESS satellite. They are actually, this is what they're measuring, these very, very tiny changes in brightness that result from the planet passing in front of its star. So here's Kepler. This is a satellite launched, I believe, in the mid-2000s, and its purpose was to kind of gaze essentially at one spot in the sky, measure the light from a bunch of different stars, and then see if it could find candidates for exoplanets, right? Stars that had little tiny changes in their brightness. This is doesn't sound that easy to me, and it's actually less easy than it sounds, because stars change brightness for a lot of different reasons. They got spots on them that can cause the change. They swell up and get smaller. They orbit around each other. So there's a lot of things out there that produce variation in the light of stars, and you're looking for a tiny, tiny, tiny amount of variation. But nevertheless, the Kepler satellite and some of its follow-ons have been quite successful. Kepler was actually a pretty good-sized telescope. It's deactivated now, I believe. It's no longer functioning. But it was a fairly large telescope, so it could kind of see a pretty deep field. But it can only really look at one spot in the sky. So this was the Kepler observation field, the field of view right here. You can kind of see where it was. It was a field of view right here, kind of at the between Cygnus and Lyra. And essentially it just kind of gazed really intensely at one area. But it could go, it could be it was a pretty deep view. It could see stars from fairly faint magnitudes. It was also the first satellite to find an Earth-like or an Earth-sized exoplanet. So bunches of exoplanet discoveries came out of Kepler, including one that was Earth-sized. Actually made it into Jeopardy. So it was a Jeopardy question once. Another kind of follow-on mission, one that's actually still quite active now, is the TESS mission. Again, transiting exoplanet search. The TESS telescopes are really much, much smaller than the Kepler telescope. What's interesting about the TESS satellite is that it's pointable. It actually scans. So instead of just kind of gazing at one spot, it's kind of looking at a much broader view of the sky. So this is the TESS coverage map right here. You can kind of think about the sky as being like a big sphere around us, right? And you can see that there's some areas that are covered almost every day, right up here, kind of the sort of the nexus of all these scans. You get coverage almost every day. Some places, it's progressively less. Some places it's only about every 27 days. And that's important, actually, because the cadence of the measurements, how often you make these measurements, is a really important indicator of exoplanets versus false positives. So there's tons of test data. A couple months ago, we actually kind of looked at some test data during one of the meetings, and I think the last time I looked at their database, there was over 9 million observations from tests. So it's an extremely capable satellite. And as we're going to see, it actually opens up some opportunities for people like us if we want to kind of make a contribution to this. But anyway, and if you're interested in things like data mining, you can go through the TESS database on your own and kind of look for these. I've done that a little bit, haven't found anything, but it's kind of fun. So anyway, these are kind of satellite-based survey techniques. In terms of where they're finding these things, it's probably not a really big surprise. Most of the exoplanets we've found so far are pretty close to home. So this is kind of a diagram of the galaxy. This right here would be the discoveries from TESS. This would be the discoveries from Kepler. Notice that it's only in one direction, but it's much deeper. Things are much further away, right? Because of the larger telescope, and it's kind of only looking off in one direction. And then there's a few weird ones out there that are being found through micro-lensing techniques, basically using a version of gravitational lensing. So those are kind of, a little bit further away. But I thought this was a really interesting image because, there's thousands of these things out there now, and they're all in this little patch of the sky, right? Or this little, local neck of the woods, only tens, maybe dozens of light years away. And there's all this galaxy out here, so imagine how many of these things might actually be out there. It's kind of mind-boggling. I don't know, there's a nice picture. The one estimate then, based on extrapolating out the early, because these missions are still in some ways in very early phase. If you extrapolate out to the entire galaxy, they'd estimate that there's probably somewhere on the order of about 400 billion planets, which is a staggeringly large number. So plenty to do. So what are exoplanets, basically? And I think this has been one of the big surprises from exoplanet research. And we got so used to the idea that there were the types of planets were what we could see in our own solar system, which, as it turns out, are not a very representative sample in many ways of some of the things that have been seen in other places. So there's basically, depending on who you talk to or how you count them, there's 4 or 5 different classes of exoplanets now. One are the gas giants. They're similar to Jupiter or Saturn. A lot of these are are what are called hot Jupiters, hot planets. They're very close to their star, but they are essentially similar to the gas giant planets. Then there's the kind of Neptune-like ones, the Neptunids, they sometimes refer to them as, which would be similar to Uranus or Neptune. So not exactly a gas giant, more like maybe a frozen, an ice giant or something like that, and not quite as giant. And then there's the super Earths, which are bigger than Earth, more massive than Earth, but lighter than Neptune. Some of those have kind of turned out to be pretty interesting. They may actually have open water. For some of them may have free water on them. Some of them may have gases in their atmosphere that are suspicious, I guess you could say. It may not necessarily be able to just happen spontaneously. And then there's the terrestrial ones, which are rocky in the Earth size range, and then there's the ones that are even smaller than that, the sub-Earths, I think they call them, even smaller than that. So here's an example of a hot Jupiter. These are gas giant planets that are very close to their star, so close, in fact, that they, in some cases, may exchange gas with the star. The very first detected exoplanet was a hot Jupiter at 51 Pegasi b. It's been a long time since I kind of carefully studied planetary formation, but the theory that we were taught back in the 80s was that Jupiter formed nearer to the sun than it is now, and then kind of made what they called the grand tack. It moved outwards, and in the process created the conditions for the formation of a lot of the other planets. And it makes me wonder if maybe this is an early stage, like something that was, at one time maybe Jupiter was hot Jupiter. I don't really know. I haven't been able to get a good answer on that. Of course, I haven't really asked that many people that might know. But it kind of makes me wonder sometimes if this is an early stage. But anyway, it's a fairly common type of exoplanet, largely because of the availability bias. These are the easiest ones to observe. They're close to their star. They're really big. They're very easy, particularly easy to observe with the transit method, because they go across really fast. And so a lot of the planets that have been discovered by some of these transiting missions have been hot Jupiters. There's the Uranids and Neptunids, the Neptune-like ones. Super Earths, again, they're the ones that are kind of attracting a lot of attention because many of them show atmospheric characteristics consistent with the presence of water and in some cases carbon dioxide and oxygen, possibly. The terrestrial ones, again, are the most, they're the size of Earth, but they aren't necessarily like the Earth, right? They may be more like Mars, for example. And then there are actually some that aren't associated with planets at all. There's one that's called these nomads that are just basically kind of drifting around out there. They're not associated at all with stars. So unbound to a star. So those are some of the types of exoplanets. Here's just a few kind of statistics on these, how many of these and against the size. So if you put it on a scale where Earth is size 1, right, so Earth's size planets would be right in here. This is, again, this is a little bit dated, but this gives you the fraction of the observations. So about 20% of them have been Earth-sized. Probably somewhere in the order of about 50% of them, maybe 60% of them, fall into this range that would be the Earths and super Earths, basically, and then as you get out here to the larger ones. One of the things that's kind of interesting, that I found interesting about this diagram, was that some of the largest number of observations have actually been on objects sizes that don't occur in our solar system. You know, we really don't have anything in our solar system that would be like a super Earth. So, and they may be a type of object that is completely unfamiliar to us.
Has this been adjusted for observing bias, do you know?
That's a really good question, and I don't. I'm not sure the statistics are good enough yet.
Yeah.
But that, I mean, that's a really good point, because there's a built-in bias to this, because some things are just easier to see than others. So Yeah, that's a really good question. So here's one I wanted to just kind of point my finger at here a little bit. This is Kepler 186f. This was discovered by the Kepler satellite, or using data from the Kepler satellite. And this is a Earth, it's a terrestrial-sized planet, but what is really interesting about it is it's around a smaller star, a smaller, dimmer star. So if you could watch, sunset on Kepler 186f, it'd be a lot redder. It's a lot redder star, basically. But here's the thing that's kind of interesting about this. There's some evidence that there may be reddening on the surface of the planet itself. And again, this is very speculative. Nobody's, I think, nobody's ready to form a conclusion on this. But it could possibly be due to some organism that's doing some equivalent to photosynthesis, except at different regions of the spectrum. So there's this little poster here that NASA made a bunch of these posters. Kepler 186f, where the grass is always redder on the other side. So there's some speculation that there may be a biosphere here that operates at wavelength. Photosynthesis, the reason why stuff is green is because photosynthesis needs red light and blue light and not so much green light. That's why vegetation is green. This may be something that's shifted to a different part of the spectrum. It's still really speculative, but it really kind of, I don't know, it's an idea that I think really, I found really, really interesting.
That said, that the redder stars have a tendency to be more reactive and can produce a lot more radiation in bursts that kind of control life as we know it.
Yeah, it may be really hard for some kinds of evolution to happen on those because, yeah, they're kind of unstable stars. On the other hand, they got a lot of planets around them.
Yeah.
So, yeah.
They have a lot of numbers.
Yeah. So anyway, like I said, the detection thing for a long time was the sort of the game in exoplanets. There was space missions to detect them. There were ground observation programs to detect them. But more recently, it's moving more towards not detecting them, but actually figuring out what their properties are. And that's where I think some of the most fascinating part of this is actually happening. Finding more and more exoplanets in what would be the habitable zone of their particular solar system. They define the habitable zone as places where liquid water can exist. And there's a little bit of a bias there as well because liquid water is so important to life on Earth that we just assume it's going to be important everywhere. But there's some pretty good arguments, I think, to kind of support that. So, they sometimes call it the Goldilocks zone, right? The place where temperatures are just right. And it's turning out that there's a number of detections and observations of exoplanets that are in the habitable zone. This is one that kind of attracted some attention. There was actually an article about it in USA Today. I guess when you've made it into USA Today, you've made it, basically. Earth to 452b. So this is one that could be a pretty good candidate for life. They call it. It's a super Earth, a little bit bigger, probably a little bit older, but it's showing some evidence that it's atmospheric evidence that kind of suggests that there could possibly be an abode of life. So this is what it would look like, relative to our solar system's planets. So here's ones that have been found. Again, this is a little dated here. Again, sorry, I stole this guy's slide, so I shouldn't be complaining. But as of July of 2015, these were the stars. These were the planets that Kepler had found that were small, like not small enough to be in the range of Earth, super Earth, and in the habitable zone. There were two around G-type stars. Kepler 452 was one of them. That was one of the reasons it attracted some attention. The sun's a G-type star too, so it was similar to the Earth in that respect. There was 7 of them around K-type stars, and 4 of them around M-type stars. These are smaller, redder and dimmer stars than the sun. So that was, I think, what was kind of noteworthy about that Kepler 452b discovery. And again, the search in some ways is starting to turn towards life, towards finding evidence of life. The way that that's typically being done is to look for to look into the atmospheres, and what they're essentially looking for here is mixtures of gases that can't remain stable by themselves. And the Earth's atmosphere is a really classic example of that. It's out of chemical equilibrium, right? If you mixed all the stuff that the Earth's atmosphere is made out of in a big jar or something, it wouldn't remain stable. It would start reacting down to other things. And what maintains the composition of the Earth's atmosphere is the biosphere. And so that's kind of the basic idea that astronomers are trying to use. So trying to use, really, really sophisticated observational techniques to look at the atmosphere of one of these. And the technical virtuosity of this is really mind-boggling to me. But this is becoming where the exoplanet field is kind of going. So here's a kind of an example of that. This is a spectrum that kind of shows features of an exoplanet atmosphere. And these little dips right here are absorption bands, right? This is where various constituents of the atmosphere absorb light. And so this is the kind of where the field is now. I think that the more interesting stuff is trying to detect these signs of life. So there's an oxygen band right there, there's a water band right there, and there's a methane band right there. So that would be, those would be things that would be pretty good. Not QED certainly, but pretty strong evidence that there's a biosphere operating here. Okay, so what else? Okay. So there's a lot of interest in this. So there's a whole bunch of new space missions that have been kind of proposed for this. This is kind of a history of all that. So there's Kepler, there's TESS. Of course, the Webb Space Telescope, one of the things it's designed to do is observe exoplanets. This W first one is the one that I think is going to be really interesting, actually. So here's the W first. It's going to do a survey for dark energy, an infrared survey, and an exoplanet census, including imaging and spectroscopy. So the current generation of exoplanet observers, they can only do photometry, right? They can only do those measurements of brightness. This thing might actually be able to do direct imaging and spectroscopy. This is like a lot of other, this is actually a joint project between the European Space Agency and I think NASA is involved a little bit too. And like all these other aerospace things, it tends to run way over budget and way behind time. So, this may not make it into orbit for a little while yet, but it's, I think when it gets past being concept and actually being in orbit, it's going to be pretty interesting. You got any information on it?
I think it's called Nancy Grace Roman Space Telescope now.
Right. Yeah.
Oh,
yeah.
okay.
And Nancy Grace Roman was a pioneering woman astronomer. Yeah. So now the Roman space. And when did they have a launch date or a
2027.
Yeah, that's about. Yeah. So this could here in a few years this could be providing us with some interesting information. Okay. So this is the New Worlds telescope. It's the one that's actually going to have a star shade. It's going to be launched in 2 parts, and the star shade will be a long way away, and they move it in front of the star and then observe it with the HABEX, the Habitable Exoplanet Imaging missions. So I think this, it's going to be really fun to watch all of this stuff happen over the next decade or so, I suppose. There's the LUVOR. They come up with some interesting names for these things too. The LUVOR is a ultraviolet optical. This is, the Webb is infrared, right? It's long wavelengths. This thing's ultraviolet, it's short wavelengths. And and designed to look at things like atmospheres and that sort of. Kind of looks a little bit like the web. All right, so these are the huge, expensive telescopes that that the astronomers will get to play with. What about the rest of us? It actually turns out that amateurs can really make a very significant contribution to exoplanet work. All these detections that things like TESS and Kepler and all these other programs, there's a pretty high chance of a false positive. There's a pretty high chance of thinking that, hey, there's something there, and there really isn't. Turns out, it's a star spot, or it's something else, a slight variation, a slightly variable star. And so there's a real need for kind of following up on these things. And again, this is kind of a niche where you don't need state-of-the-art equipment to do this with. Here's a pretty good example of this. This is a guy that lives in Fremont, California. This is his observing equipment. This is an 8-inch Meade telescope. He's got probably some kind of SBIG camera on here. This whole rig right here, if you bought everything brand new, would still, I don't know, like $3,000 maybe. Very modest equipment. And this is a light curve that he got from a transiting. And what's needed here is follow-up observations to, first of all, establish the ephemeris, establish the timing of these orbits. Sometimes finding companion planets, right? There you can actually determine whether there's more than one of these things by timing variations. Looking at the stellar activity itself, and then there's actually some amateurs now that are detecting transits of planets by radio velocity techniques. This again is it's a much more difficult kind of measurement, but there's this group called SpectraShift now, and they've actually built a spectrograph that can do those kinds of those radio velocity measurements. Here's some of their data right here. They looked at a known exoplanet, and this is their work, right? And this is a professional survey, and you can see the orbital elements are really pretty similar. So they've been able to actually.
If you go back one slide, is each one of the dots horizontally, is that a night of observation?
No, it's probably a cadence more like hours, I would guess, maybe even.
Okay.
It's a one night.
Yeah, this is over one night.
Yeah.
So that's saying in that one night he saw the star dim.
Yep. And then this, the blue ones are differential magnitude, and then this is corrected for a limb darkened model. Like if you look at a star, it's always darker around the edge because it's curved, and that can kind of affect the brightness measurement, so they compensate for that. I actually took Gary mentioned the AAVSO, and the AAVSO, the American Association of Variable Star Observers, whose slide has vanished on it. Gosh darn it, sorry. I made a slide to show you their contribution, but they have an exoplanet observing section, and there you can report your data to them, and they actually teach classes. I took a class in exoplanet observation. It was really interesting stuff. It's actually something I'm really kind of anxious to do, but unfortunately my day job sucks up a lot of my time.
Are they stressing differential photometry for this, or is this all Skype?
Most people do differential.
Yeah.
Not too many people, I think, are really set up to do all sky.
Well, it puts in a lot more complication for doing this.
Yeah, there is a guy in Arizona. I think I was gonna show his book. It's kind of a guy named Bruce Gary, and he's a retired radio astronomer who decided to become a hobbyist optical astronomer after retiring. And he wrote a book on this, which I have an e-copy of it if anybody's interested in it. It's a PDF file I could send you, but he is able to do all sky photometry. He's works in southern Arizona, like as far as I can tell, he's down south of Tucson somewhere.
Wow.
So they probably have stable enough skies there and enough transparency to make it a little bit easier.
Yeah, it is a real difficult thing to do all skyphotometry in our area, because
Yeah.
our atmosphere is just not very cooperative.
Anyway, I thought I'd close it off with a Carl Sagan quote, though. You know, all those other worlds, are they looking back at us? So, anyway, it's a little bit about exoplanets.
Isn't that a picture of Earth?
I think it is, actually. It was taken from one of the deep space probes
Mhm.
looking back at the Earth. Yeah,
This is the pale blue dot.
pale blue dot. Not a very good picture.
I think it's like one of the rings of Saturn or something.
That sounds
Or
right.
Jupiter.
I was reading something, by the way, about the rings of Saturn. They're much thinner than I thought. I always thought of them as being several tens of miles thick. They're actually
Yeah,
much of a distance.
Yeah, yeah.
They had there was a graphic of how, if you were in them, how dense the stuff around you would look, and it was.
Is that about 1 to 2, was it, not 1 to 2 kilometers, but several hundred meters?
Yeah,
I mean,
it's
not very
really,
big.
really thin, yeah. Anyway, that's all I have. Questions, comments?
so how long do you think it'll take to get your spectrograph at Farpoint?
Well, at the rate it's going, forever, because I haven't made any progress on it. But that one I'm not sure would be quite have the resolution to do the radio velocity stuff, even if it does get built. I do want to get on that. It's just, it's at the bottom of a huge list of things to do.
I will say, I think people that want to do verification of these exoplanets, it's actually not that hard to do.
I don't think it really is. I mean, people are doing
It's
it
just a
with
matter of a long time starting in one spot.
yeah, and people are doing this with really modest equipment.
Yeah.
There's a guy that set up a kind of an automated system to do it, and he used like a 10-centimeter refractor, which is what.
Peter up in England is turning in some data that's in
Mhm.
publications.
Yeah, yeah, yeah.
And,
There's life after astrometry.
well, I mean, and this is the sort of thing that we could do.
Yeah.
I mean, I think we have the capabilities.
Is he using Tycho Tractor or?
No, he's not. Matter of fact, I talked to him. There's a program now that's put out by Catalina Sky Survey. I'm going to diverge from the topic here. That for running up NEOs and doing follow up on NEOs. That looks like a program that he would have